Hello, everyone. Today, I am going to present a framework for analyzing offshore wind energy's potential indirect impacts on hydropower operation and migratory fish. We are focusing our analysis on the New England region, which is in the northeast quadrant of the United States. And we are focusing here because they have a lot of things going on in terms of transition, and offshore wind energy deployment has been seen as a potential driver for the states to reach their 100% renewable energy goals. Currently, there is 5.5 gigawatts of coal and oil capacity that are at risk of retirement in the New England region. So that makes this region a prime candidate for energy transition analyses. Two key studies that we build off of are Max in 2013 and Klein and Willey 2015, where those two studies looked at individual technologies and asked which one was the most sustainable. But one thing that we know is that the sustainability of the whole system is not necessarily equal to the sustainability of the parts of that system, because there will be impacts that individual technologies have on each other based on the way that they're interacting with each other and operating with each other. So we need to capture these interactions in sustainable energy analyses, and then this can also help inform what those ecological impacts are. Normally, when people think of offshore wind energy, we tend to focus on the direct impacts. Again, that's taking that singular technology view, where offshore wind energy can, build habitat gain for juvenile fish. There also may be acoustic disturbances during the drilling phases. But there is a question about what are the indirect impacts that can result from a changing energy system. So let's dig a little deeper into that. So if you have offshore wind getting built in the New England region, then spikes and falls in this wind energy may be balanced with hydropower. And then that hydropower, like generation spikes, will impact river flows. And those river flow changes can impact fish migration. Here, when I am talking about hydro, I am talking about a traditional hydropower plant, which in our case is a run-of-river hydro plant. Water is fed in at the top of the river. It feeds off into this penstock or tunnel, which then goes into a turbine or generator. And that will cause the turbine to spin, generating electricity to send back to the grid and then feed out into that lower river. And so that is how we are saying it can affect the river flows with these spikes and falls in generation. There are multiple hydropower plants along the Connecticut River. Each circle represents a traditional hydropower plant, and each triangle represents a pumped hydro storage facility. And just a key thing to note is that these dams seriously impede fish migration and present multiple change points for river flows. And that can seriously impede fish migration. So some studies have found that fish avoid migrating during changing flow magnitudes. And to minimize the ecological impact, it is recommended that discharge be stabilized during the spawning period. So that actually, presents another challenge for a 100% renewable energy system, because now you're needing to take into account how the wind variability is going, as well as when the fish are migrating. And that can actually, impede the ability of some of these hydropower facilities to balance, provide balancing capabilities for wind energy. We investigate include 9 different fish species in our analyses, and that's presented in this table here. At the top row, we have the months of the year. Then the check mark just represents if the fish is reported to be active in that month. And then at the bottom, we have the total amount of active fish species during the different months of the year. So one thing that we noticed is that the fish are most active during May and June. And so those would be 2 key months to watch out for the interaction between offshore wind energy variability and hydropower variability. So the fish species under concern, we do recognize that they're not going to be active along all parts of the river at all times. And here is a map of the Connecticut River and its tributaries. showing the number of fish species under concern. So the darker the point on the map, the more fish species under concern. And we see that the most fish that we're concerned about are going to be at that bottom of the river, that first intake point. And then as you move up the river, you have less and less fish species of concern. And that has to do with the fact that dams have been impeding fish migration. So you're going to see less activity. We also see that the number of species with high spawning seasonality, it does vary across the Connecticut River, where there's a lot of spawning occurring in the middle and upper regions of the river. And that is going to also be something that hydropower operators will need to take into account, because this will impact the ability of juvenile fish to have a healthy environment to grow. This flowchart is presenting our methodology for combining an electricity system model in the blue side with an ecological impact analysis on the yellow side. So first, what we do is we take in hourly demand of renewable resources, and we also have other generation constraints like nuclear outages and maintenance. Then we take initial generation capacity levels. We feed this into an electricity model for our future system and determine if that system is reliable, meaning can it supply energy at all hours of the year. If it is deemed not to be reliable, then we report that we need to add capacity and that portfolio is no longer included in our analysis. And if it is reliable, then we output the energy by source. We calculate the changes in hydropower generation under those varying levels of offshore wind. We then use that to calculate the changes in river flow. And we use that, and then we investigate how river flow changes correlate with migration periods. The key assumptions in our energy model are that this is a resource adequacy problem, meaning that we just need to ensure enough generation capacity satisfies demand. And this generation capacity includes natural gas, hydropower, nuclear, solar, wind farms, and oil plants. We exclude coal because it has, by the time that our analysis is set in 2035, which ISO New England is projecting to retire all of their coal capacity by that time. Here is a more detailed look at our electricity model, which is based on a merit order for dispatch. So what it does is we start with an hourly demand at time T. It first dispatches nuclear, followed by solar and onshore wind, followed by offshore wind. It then checks to see if there's any hourly demand left. If there is, then we dispatch natural gas and hydro based on historic splits in the New England region. We determine if the natural gas pipeline is maxed out. If it is not maxed out, we assume that we're in the summer and it will dispatch hydro if there's still demand left, followed by natural gas and oil. Then if the pipeline is maxed out, we assume that we're in winter, meaning that the natural gas, meaning that the hydro river will need to actually have a higher level. So we'll first dispatch oil, followed by natural gas. And if there's still hourly demand left after we've dispatched all of our power plants, we say that this portfolio is not going to be reliable and we need to have more capacity. And so then we would exclude that unreliable portfolio from our analysis. We measure hydropower variability using the following equation, where hydro variability, or in other words, the ramp, is equal to the hydro generation at time T plus 1, subtracted from the hydropower generation at time T. Here is the output of one of our analyses. So this is going to be the case where we have low wind deployment in the New England region. So that's going to be 1,600 megawatts. And that's just 7% of the hours will have a ramp of greater than 2 megawatts. So here we're seeing our generation, and along the y-axis, the x-axis is the hours in the year, and the red lines represent the 10th and 90th percentile of all the hours that we're ramping, and the blue represents the ramp. Now we see this change a lot as we are increasing our offshore wind. So when we move into our high wind scenario, which is 10,000 megawatts of offshore wind in the New England region, we now see that 19% of the hours have a ramping range greater than 2 megawatts. And this is going to be very important for understanding those ecological impacts or implications, because we see that we are now seeing a lot more periods with very low generation as that offshore wind energy is displacing the need for hydro, and hydro is going to spike a lot more, which means that the river flow can have greater spikes. So in general, we see that the ramping needs widen with offshore wind capacity. Along the x-axis, we have the offshore wind capacity deployed in the New England region in megawatts. Along the y-axis, we have hydro generation in megawatt hours. And we do see the widening of the curve. Specifically, the daily low is dipping down much wider as we have offshore wind capacity increasing in the region, whereas the daily peak is remaining relatively stable. This graph is showing you how the hydro ramp and fish migration are related. Along the x-axis, we have the different months of the year. Along the y-axis on the left-hand side, we have the number of active fish species, which corresponds to those gray bars. And then along the right-hand side, y-axis, we have the absolute hydropower ramp. And the red triangles represent the low wind scenario with just 1,600 megawatts of offshore wind capacity deployed in the New England region. And the blue circles represent the high offshore wind capacity deployment, which is going to be that 10,000 megawatts. And so here we see that the absolute hydro ramp from 1 hour to the next is seeing the greatest increase for both the high and low wind percentile deployment in January to April. So that is actually a good sign for our ecological impact correlation, because these are going to be periods of low fish activity. Whereas, here we see that we also have relatively high absolute ramp in May and June. And so one thing that we would want to make sure is that we do have enough other technologies to compensate for limitations in hydropower generation that will occur to minimize ecological impacts. So we also need to connect this to river flow impacts. So the average hourly hydropower output in megawatts is going to be equal to the density of water multiplied by gravity times the maximum dam height above the river, multiplied by the mass flow rate of water through the generator. And so here we see that the hydropower ramp of 4 megawatts, or that 90th percentile of high wind, would increase the river flow by 800 cubic feet per second. And that can lead to a change in river elevation of 0.026 feet per hour. Now, this elevation is safely within the bounds of the operating limits, but we note that a large portion of wind variability in our model is absorbed by natural gas. So all of that wind power availability was not absorbed by hydro, only the natural gas would accommodate for the majority of the variability absorption in our New England region. And as we are moving to 100% fully renewable energy system, this hydropower absorption would become greater and greater, especially as it's replacing natural gas. And so that is something that would need to be taken into account, because we could see much higher changes in river elevation, especially as we are seeing greater spikes. So in conclusion, our results indicate that an increase in offshore wind capacity will lead to larger ramps in the river. This may adversely impact fish due to during their spawning times as well as their migratory times. We find that the average ramp in hydropower operation increases linear with the capacity of offshore wind, with the minimum level is reduced frequently. As a caution, New England is a natural gas dominated system, meaning that a large portion of wind variability would be absorbed by natural gas. And so that should be taken into account as we are thinking about those ecological impacts of a fully renewable system. I would like to thank the National Science Foundation for helping fund this work. And this paper has been published in Renewable and Sustainable Energy Reviews. So thank you very much for listening, and I hope that you guys have a wonderful conference.